Welcome back to Mechanical Systems Design. Today we're going to talk about energy loss, and we'll focus mostly on energy loss due to sliding dry friction and wheel rolling resistance and collisions. It'll help, as usual, to have read the topic reading first. We'll do a little bit of a review and then do some exercises, so it'll be good to have pencil and paper and a partner if you can connect up with somebody to make it more interesting. Before we get started, a mystery. So we have these two septagons, and you can't feel them, but they feel about the same. They have about the same mass and surface touch and look. But when we go to roll them, one stops quickly and one goes for a long time. Let's see that again. So our mystery here is, what is it about these two septagons that makes them behave differently? And if you want to ponder that now, you can pause. We'll come back to this at the end of the video and unravel it a bit. And that's not our only mystery today. We have another mystery, which is the mystery of the silicone lid. So here we have a silicone rubber lid from a popcorn popper. If we spin it on its little handle, it goes for quite a lot of rotations before stopping. But if we kind of throw it to slide across the table, it doesn't translate very much before stopping. And so the question is, why does the lid slide so little but spin for so long? And here again, you can pause if you'd like and ponder that, write some things down, and we'll come back to this at the end of the video to talk about it. All right, now let's review energy loss. So most of us have a sense of what energy is. It's this potential to do work. And so the way that we change the energy in a system is to do work on it. We can recall this from our physics mechanics course. And so mechanical work is defined as force over displacement. And if that force is constant, then it's just, the work is just F times the change in the position, F dx. If the force is varying over space or time, then we need to integrate, and work will be the integral of the force with respect to displacement. And the same thing applies to rotational systems. So work is equal to the torque times the angular displacement if the torque is approximately constant. As we do work on a system, it will change the mechanical energy of the system. And there are two ways that the energy can be stored. One is through potential energy. For example, gravitational potential energy, mass times gravity times height, or mgh. Here, if you look at this, you'll notice it has exactly the same form as our work equation. We've got mg, that's a force, that's the weight, and a height, that's the change in position in the vertical direction. So if we wanted to change the potential energy of an object, we would lift it, right? And that would be applying a force equal to its weight over some displacement equal to its height. So these things stick together. And this is a really good equation to remember as you think about what is energy. We can also think about potential energy for things like springs and really any force field. For the special case of a spring that's linear, we have that the potential energy will be 1/2 k delta x squared. And how we get there is, we can see it's secretly just this form, except that the force, instead of being constant over displacement, starts at 0 and goes up to some maximum value as it's stretched. And that value will be k, which is the spring constant, times the displacement, so k delta x. And so the area inside this triangle is k delta x times delta x and 1/2 of that, because it's not the full square. The other way that energy can be stored is as kinetic energy. And we just remember this from our physics course. The kinetic energy is 1/2 mv squared. And equivalently, in a rotational system, we have that the kinetic energy is 1/2 I theta dot squared in a planar rotational system. Now, power is just the rate at which work is done. So it's the rate of change of energy in the system, or the time derivative of work. So if we just go back to our work equation and we take the derivative of both sides with respect to time, we get the change in work per unit time is the force at that instant times the change in position per unit time, or the power, mechanical power, is force times velocity. And we saw this in our motor analyses, right? Equivalently, we have that the power could be the torque times the angular velocity. And in electrical systems, which are kind of analogous to mechanical systems, we have that the power is the voltage times the current. And I like to think of this as the voltage is this electromotive force, which is an early term for voltage, that's trying to push electrons through your circuit. And the current is kind of like the speed. It's how fast electrons are moving through the circuit. So it's really kind of the same equation. So friction losses, which we're going to see in a lot of our designs in this last project, it's just a special case of work that where instead of just any old force, we have a force due to friction. And we could model this as dry friction or Coulomb friction, with the friction force being equal to the coefficient of friction times the normal force. And then the displacement is just the displacement of the sliding contact point. So where the two things touch, how much they move relative to each other is what's going to determine the displacement and the energy loss to friction. So if, for example, we look at the energy lost due to a rope being routed around an eyelet where it's going to slide along this piece of material as it moves, what we do is we'd want to perform an analysis to figure out what is the normal force. And we've got a version of this in the topic reading. A super simple version would be to say, oh, this looks like it's about ignoring the drop in tension. You would say, oh, square root of 2 times the tension in the rope, and multiply that by mu to get the friction force. And then you'd say the amount of displacement multiplied by the amount of displacement to get the work that is going to go into heating this eyelet instead of being transmitted to the next element in your system. So that this kind of illustrates the general technique here. To get coefficient of friction, we're going to either look it up in a book or perform a sliding test to figure out what it is. And then we're going to perform a free body diagram analysis of the element in our system to figure out what is the normal force. And then we'll just do a little bit of geometry and algebra to figure out what is the amount of displacement of the surface. Sometimes it's really simple. Okay, another important loss source in our mechanical systems is wheel rolling loss. And this is a special case where we have a torque that arises because of deformation of the wheel. So if we look at the wheel as it's pushed onto the ground by some radial load, maybe from a shaft that's pushing it down on a bearing, and maybe that shaft is supporting the weight of a robot or a payload or something, then the normal shape of the wheel would be like this dotted line. But in order to have a finite contact patch with the ground, the wheel has to squish a bit. And so we get this flat shape and a pressure distribution that looks something like this between the wheel and the ground. If we then try to make the wheel roll, then because of sort of pinching and shearing of the material, and because of hysteresis, as the material is squished and then recovers, that we're going to get some material bunched up on the front edge of that contact with the ground. And that will cause this pressure distribution to shift forwards. And so now that normal force is no longer collinear with the loading force at the center of the wheel. It has some lever arm about the center, and that means it causes a moment. And so we're going to have a rolling resistance that is going to be proportional to that normal force times the radius of the wheel. And then the amount that this the center pressure creeps forward relative to the total wheel radius is going to be captured by this coefficient, the coefficient of rolling resistance. And this is a function of the materials involved and the speed of rolling and things like that. But generally, just as some sort of back of the envelope guidelines, the coefficient of rolling resistance for a ball bearing, two hard metal surfaces rolling together is like 0.001, really small. For a bike tire, 0.005, and for a car tire, more like 0.01. And you can get into the tenths area if you start adding things like going through sand. So that's how we can estimate energy lost due to rolling resistance, and it'll end up heating the wheel. That's where the energy will go. Another interesting case for wheels is the collision that happens when you hit a bump. So as you're rolling along, when you all of a sudden hit some bump in the surface, there's an impact. And before the impact, you are going forward. After the impact, you're going up at some angle. And all of the momentum that's along this line of the impact gets lost. And so, and it all happens very fast. So there isn't a lot of, this is all a kinetic energy calculation. And so we can model it using impulse momentum ideas, and we go through this in the topic reading. But the big take home point is that we're going to lose some energy every time we hit a bump. And the amount of energy that we get to keep will be approximated by the radius of the wheel minus the bump height squared divided by the radius of the wheel squared. And what this tells us is that if we would like to roll with minimal energy loss due to collisions due to an uneven surface, and every surface has some little bumps, then we'd like the radius of our wheel to be big compared to the size of the bumps on the surface. Okay, so that is a quick review of some of the key concepts from the topic reading. It's a lot to take in, so this is a good time to take a little break, walk around the block, stare out the window, stir your coffee, and when you've reset, come back and we'll do some exercises. All right, refreshed and ready? Next, we're going to do some exercises. And we're calling this instant replay. And what we have here is some prototype jumping robots from a previous offering of the course. And we're going to look at some of these prototypes and try to understand what the power losses are and how we might estimate them and see if they're big or not. So here's our first robot. And I want you to focus on this release mechanism. So what's happening is there's a motor up here, it has a drum, it's reeling in this rope. And then that rope is tied to this ring that can slide along this lever. And the lever can also slide along this shaft in one of the legs. And eventually, as it gets very near the bottom, that lever can slip off and the whole robot will jump up into the air. So let's watch that one more time. And I want you to think about, specifically thinking about this release mechanism. Where could we lose energy? How could we be dissipating energy? All right, you getting some ideas? All right, so the first thing we're going to do here is think about our high-level strategy. Where are we going to lose energy and why? And then what model will we use to estimate it? And then what things do we need to estimate or calculate in order to estimate that energy loss? So what I want you to do is take a couple minutes and just think that through, write some things down. You might write down an equation, say, and figure out what it is you need to identify. All right, that should take a couple minutes and you should hit pause now. All right, do you have a strategy? Hopefully that involved thinking about places where we could have sliding energy loss, energy loss due to sliding friction. And so we're going to want to have the friction force, which would be mu Fn, and some kind of displacement. And then to get the normal force, obviously we're going to want to do a free body diagram. So what I'd like you to do now is actually go through that process symbolically and try to end up with an equation that says what you expect the energy loss to be from all the places that we lose energy in this release mechanism, right? That should maybe take 5 or 10 minutes. So start working on that and hit pause now. All right, did you get something? Well, here's one version of this analysis. So I chose to do a free body diagram of the lever and to try to get at the losses both from the ring sliding along the lever and from the lever sliding along that pin in that one leg. I'm going to skip the energy loss due to this hinge point because the length of the lever is pretty big compared to the radius of the pin over there. So we're just not going to, we have this big mechanical disadvantage for the friction, and it will turn out to be negligible in this case. So we've got our free body diagram, and we are interested in this friction force and its displacement. So we need the normal force. I'm going to say that there's this normal force here is the force from the ring, and that we know what it is in this case, because that's going to come from the torque on the drum that's connected to the motor, or you could get it from, say, the rubber band and the geometry of the legs. So let's say we know what this ring force is. The sliding friction force for that first contact will just be coefficient of friction times the ring force. Now we need this normal force over here so we can get at this other sliding friction. And in this case, we can just do a moment balance about this point. And we'll say that these friction forces are approximately through that point, so they don't contribute anything to the moment balance. And that means that we've just got this ring force and this normal force. And the ring is about halfway between the contact point over there and the contact point here, the hinge point here. And so this normal force has twice the lever arm, so we need 1/2 the force to get the same moment. So the normal force here will be 1/2 of the ring force. And then we can think about the displacement. So I'm just going to need to look at the geometry to figure out what this distance is, and I could measure that. But I also need to know the displacement of this ring contact point. And there we'll use the fact that it's about halfway between that sliding point and the hinge point for this lever again, to say that the displacement of the ring is about 1/2 the displacement of the tip of the lever. Okay, that's all we needed. Oh, one more thing we'll say. Let's assume that the coefficients of friction are the same. So now the total energy loss will just be the sum of the two energy loss components. We've got mu Fn times d tip plus mu F ring times d ring. And well, the normal force will be 1/2 the ring force, and the displacement of the ring will be 1/2 the tip displacement, 1/2 plus 1/2. So we just end up with energy loss being about the coefficient of friction times the ring force times the displacement of the tip. And hopefully you had some similar kind of estimate that you came up with. All right. So now, is this big or not? We've written down an equation symbolically for what the energy loss would be, but should we care about it? Should this be something that we focus on in trying to make our system more efficient? Maybe it's negligible. So what I like to do now is try to come up with an estimate of the energy that you care about in the system, and then compare that to the energy that's going to be lost in that release mechanism to see if it matters. And something that can be really helpful here is to notice that there's this checkerboard background, which can help you to estimate relative displacements of mechanical systems. All right. And this should take, again, 5 or 10 minutes. So hit pause and start working on it now. All right, were you able to grapple with that and think through how you could start to estimate the energy that you care about so you could compare it to the energy loss? Well, in this case, what we are looking for is some common term shared between our two energy calculations. And what we can notice is that the work done by the motor on the rest of the system is going to be the force in this string times the displacement of the string, right? So we've got a force and a displacement, that's work. And that's a useful work because that's the work that's going to, say, stretching this rubber band or something like that. And the nice thing is that that includes the ring force that we had in our previous calculation, so we can more easily compare them. So the work of the string here, we're saying, is the force of the string times the change in length. And these two forces, the ring force and the string force, are really the same. And so the percent loss of energy will be the energy loss divided by the string work. And we previously calculated that our energy loss would be mu d tip times f ring. And then we just said that our useful energy will be the change in the string length times the ring force again. Hey, those cancel. And we're left with the percent energy loss being simply coefficient of friction times the displacement of the tip divided by the displacement of the string. So is that big or not? Well, we could make some substitutions in here to find out, get a numerical answer. And if we look up the coefficient of sliding friction for, say, steel on a rough wood surface, we're going to get something like 0.3. The tip displacement based on those images is about 1 checker, and the change in the string length is about 2 checkers. So that means we've got 0.3 times 1/2, about 15% energy loss, which is, pretty substantial in a system like this. If we somehow reduced that energy loss, we could, say, jump 15% higher, perhaps. Okay, so how could we reduce that energy loss? So what I'd like you to do now is just think about ways that we could reduce it, and consulting the model could be really helpful. And there are a bunch of different terms in it, so think about how you could address any or all of them, all right? And we'll work on this for maybe 2 or 3 minutes. So hit pause now, think up some ideas, and then come back and we'll discuss. All right, you have some ideas. So there are a bunch of possibilities, but some that commonly come up are to use a different material so that we reduce the coefficient of friction. Certainly that would work. If we're trying to reduce friction losses, it's always helpful to get a lower coefficient of friction. You can do that through material choice or by using an explicit bearing or other roller. And that gives you a lower effective coefficient of friction because either of changes in leverage or from rolling without sliding. Another thing you could try is to place the latch lower on the leg, and that would reduce the displacement of that point. Or you could use different leverage that would reduce the normal force at the release sliding point. So there are ways to address all of the different terms in our friction loss equation to reduce that energy dissipation. All right, here's our next robot. And in this case, I'd like you to focus on the feet, especially during the jump. Let's watch that one more time. Think about these feet. Got it? All right. So now let's see if we can come up with an approach for estimating the energy loss due to foot sliding. So here I'd like you to, again, try to come up with a way of getting at the coefficient of friction, the normal force, and the displacement that you care about to get a sliding loss here. And very simple symbolic form is perfect for this case. So just take a moment and write down, try to get to an equation on this, all right? 1 or 2 minutes, and you should hit pause now. Do you have something? Well, this one is so straightforward that it can feel like it's too easy. But all we're looking for here is we've got some normal force from the ground, some friction force, which is the coefficient of friction times the normal force, and some displacement. And the displacement that we're going to care about in this case will be the difference between the initial position of the foot and the final position of that contact point of the foot between when it's at its bottom part and when it's just about to lift off of the ground. So the next part is where we're going to challenge ourselves really with this exercise. So once again, our question is that energy loss big? So now we'd like to try to compare the energy loss due to friction to some other energy that we care about in the system and see how they stack up. So take a minute and you can use the tile background. That could be helpful. And think about, what can I find a term that is shared between these two energies, where one is the sort of useful energy in the system and one is my energy loss, right? And that maybe take 5 or 10 minutes and try to analyze that, right? So you can hit pause now, come back when you have an answer. All right, did you get something? So there's lots of possibilities here, but the thing to see in this case is that, maybe a lot of the mass of the system is concentrated in this top element, and that thing has some displacement. And the displacement there could be related to this force if we assume a concentrated mass to get an effective work done on the center mass of the system. And so the way we're going to do this is we'll say we previously solved for the energy loss, and now we're going to say that the change in the position of the center of mass, which we're approximating as that main carriage or that the battery and motor section of this robot, is going to be our displacement. And so we have the useful work done is about 2 times the normal force times the change in center of mass. And we have these, energy loss, that's 2 times mu times the normal force times the change in the foot position. And if we take the ratio of these again, we're going to get this equation where our percent energy loss is mu times the ratio of these two distances, where one is the foot sliding distance and one is the center of mass distance. And if we substitute some values in, guessing based on the checkerboard, and again, looking up some coefficients of friction from an online source or textbook, we'll get something like 10% of the energy, the total useful energy in the system would be going into sliding friction at those feet. So again, pretty substantial. And then one last question here, how could we reduce that energy loss? So take a minute, write down some ideas, and come back to discuss. You can hit pause now. All right, you have some ideas? Well, again, there's lots of possibilities, and these are not the right answers or anything, but one way, of course, would be to reduce the coefficient of friction or effective coefficient of friction by changing materials or using rolling. And another way that you could do this would be to say, reduce that length of the leg that causes it to sort of slide across the ground. And it turns out, because of dynamics, that doesn't work out in your favor, but it does absolutely reduce the energy loss due to sliding at the foot contact. All right, now, if you need a break from the exercises, you can hit pause now, come back in a few minutes, and then we'll discuss the solutions to our mysteries. All right, feeling refreshed and ready to find out why these things happen? Okay, let's consider the silicon lead first. So we recall that when we try to slide it across the table, it stops very quickly. But when we go to spin it, it stays spinning for quite a while. And one of the big contributors to this is that when you're trying to slide across the table, the displacement of the main inertia is the same as the displacement of the contact point. Whereas when you go to spin it, you have this big rotational inertia, but a really very small radius for the friction to act at the contact patch about the center of rotation. And so the moment that is produced is much smaller compared to the angular momentum when you're spinning it versus the force compared to the translational inertia of the system when you try to slide it. So that's one big factor. And another thing that's happening is that there's a little bit of rolling probably as it tips up on the edge of that tiny little handle, such that there's less sliding happening at the contact when it's rotating than you might think at first. Whereas when you go to slide it across the table, that little handle has to slide and it can't do any rolling. All right, so that's what's going on here. How about the Decepticons? This is the really tricky one. And if you haven't thought it through yet, you have one last chance to try to resolve the mystery on your own. And you can pause and, who knows, come back to the video days later if you really want to ponder it. So let's watch the video one more time. These are an invention of my former advisor, Andy Rubin at Cornell, by the way. Super fun illustration of some concepts, some mechanics concepts that relate strongly to the energetics of locomotion, as it turns out. All right, some hints. It is not that the materials are really different. It's not that the distribution of the mass is really different. It's not a difference in compliance. All right, spoiler coming. You ready? There's a very, very subtle difference in the geometry. One of the sets of surfaces is convex, and the other set is concave. So the convex surface that's slightly, it gives you this very, very slight rolling kind of wheel shape on each surface. And so when you get to the corners, you rotate around the corner. And then when you get to the apparently flat surface, it's actually slightly convex and you roll very quickly to the next corner. And so this avoids a collision and it rolls across the table. There's a little bit of the thump, thump, thump sound. It's an uneven movement. It's the center of the wheel does not stay at the same height above the table, but you're continuously moving the center of pressure forward from one corner to the other. With the the concave surfaces, they are slightly, the surface goes slightly inwards between the two corners. And so when the next corner is about to hit, there's no continuous movement of the center pressure forward. Instead, bang, instantaneously, the direction of the velocity of the center mass of this Decepticon has to change. There's a collision. It's almost a perfectly plastic collision. A bunch of energy is dissipated, and it only takes one or two of those collisions to totally stop the Decepticon. So you might think that this little collision stuff in a rolling system shouldn't matter, and it probably doesn't dissipate that much energy, but actually it can be a dominant energy dissipation in your system. And even this very, very subtle difference in geometry can make a huge difference in performance, which is kind of cool. All right. So in summary, thinking about everything we've discussed today, when we're trying to understand energy losses in our system, what we really want to do is rely heavily on our back of the envelope analysis. We're going to use our very simple models of work and energy, and we're going to use simple models of friction and free body diagrams to understand the loading. And if we bring all those things together, we can usually find a simple symbolic approximation of the energy loss due to, say, sliding friction, very common energy loss in our systems, and then use that to, along with an analysis of the energy we care about, to see not only is that sliding loss big for the candidate system I'm looking at now, but what are the terms that I should adjust in order to make it smaller and reduce the energy loss in the system. And I think you'll find this to be a really relevant technique for the project you're working on right now. So happy designing, keep those energy losses small.